Hi, welcome back to my class in Mathematics in the Modern World. For today, we will continue the solution of the linear program we were solving last time in Lesson 5. In Lesson 5, we modified the given linear program to prepare the initial simplex tableau. And once again, this is the completed initial simplex tableau that was developed based from the modified linear program we had in lesson 5. For those of you who missed this lesson 5, just search for my tutorial video in my channel Art Kalison in the playlist for Mathematics in the Modern World, and you look for lesson 5. From the initial simplex tableau, we will now develop the second simplex tableau to search for the improvement on the values of the value of our objective function. Initially, for the initial solution corresponding to the initial simplex tableau, the values of the decision variables a and b are 0. The slump variable s1 has a value of 45. S2, the second slump variable, has a value of 70, and the objective function initially has a value of 0. Now we will try to improve the value of the objective function from 0. And to do that, we have to have some values for one of the two decision variables. For the second simplex tableau, we determine which of these two decision variables will enter in the basis column. Sorry, this should be S1. This should be S2. And C stands for coefficient. Coefficient of S1 in the objective function is 0. Coefficient of S2 in the objective function is 0. Again, the first step to develop the second simplex tableau is to determine which of the decision variables will enter the basis column, so that one of the decision variables a or b will have a value that will give an increase in the value of the objective function. And to determine which of these two variables a or b will enter the basis column, you look at the last row, the entries in the last row, c sub j minus z sub j. And you select the most positive entry, the highest positive entry in the last row. In the last row, the entries are 6, 7, 0, 0, and the highest positive entry or the highest positive number among these four is 7. And 7 is under the decision variable b. That means the decision variable b is our entering variable. Our variable b or our decision variable b is our entering variable. And to determine the entering variable, you look at the entries of the last row and select the most positive entry in the last row, the highest positive entry. And the highest positive entry among these four entries in the last row is 7. And 7 is under the decision variable b. Therefore, b is our entering variable. The entering variable is the variable with the most positive entry, with the highest positive entry in the last row. Because B is our entering variable, in the second simplex tableau, B will enter the basis column, which means that B will now have a value in the second simplex tableau. Now, for the decision variable B to enter the basis column, one of the variables in the basis column, either S1 or the slack variable S2, will go. One of these two slack variables will have to go in the second simplex tableau to give way for the decision variable to enter the basis column. And that variable, either S1 or S2, that will go is called the leaving variable or outgoing variable. And how do we determine the outgoing variable or the leaving variable? To determine the outgoing variable or the leaving variable, you divide the entries of the last column, the S column or the solution column, by the corresponding entry of the B column, the column that contains the entering variable. Again, to determine which of these two slack variables will be the outgoing variable, divide the entries of the last column or the solution column or column S by the corresponding entries of the B column, the column of the entering variable. 45 divided by 5. Again, to determine the outgoing variable, divide the entries of the last column or the S column or solution column by the corresponding entries of the B column or the entering variable. This is 45 divided by 5. 45 divided by 5 equals 9. 70 divided by 10. This should be 10. 70 divided by 10 is 7. Again, to determine the outgoing variable, divide the entries of the last column by the corresponding entries of the entering variable, the decision variable B. 45 divided by 5 is 9. 70 divided by 10 is 7. And now, among these quotients, among the quotients, you select the smallest positive quotient. Select the smallest positive quotients among the quotients. In the selection, we do not include the negative quotient, the zero quotient, and the undefined or not defined. Because in some instances, you will have a constant divided by 0, and that's undefined or not defined. And we will not include that in the selection of the outgoing variable. And also, the negative quotient is not included in the selection of outgoing variable. And also, the zero quotient. To determine the outgoing variable, we only consider the positive quotients. And among the positive quotients, you select the smallest positive quotient. Select the smallest positive quotient. And in case you have a tie, or in case you have two or more, the same, equal, smallest positive quotient, you can take any one of the equal smallest positive quotient. In our example, we have only two quotients, 9 and 7, and both are positive. So we select the smaller of the two quotients. And the smaller between 9 and 7 is 7. And 7 is in the row of the slack variable S2. Slack variable S2 is our outgoing variable. The slack variable S2 is called the outgoing variable or leaving variable. It is the variable with the smallest positive quotient in each row. Again, to determine the outgoing or leaving variable, divide the entries of the last column or the solution column or S column by the corresponding entries of in the entering variable. In this example, the decision variable B. We have 45 divided by 5 is equal to 9. 70 divided by 10 equals 7. And we select the smallest positive quotient. And since we only have two positive quotients, we select the smaller of the two, and the smaller between 9 and 7 is 7. And 7 is in the row of the slack variable S2, hence S2 is our outgoing or leaving variable. And why do we say this is the outgoing, why do we call S2 the outgoing variable? Because in the second simplex tableau, you will no longer see the variable S2. And because in the second simplex tableau, it will be replaced by the decision variable B. That's why B is called the entering variable. It will enter in the basis column. It will replace the outgoing variable S2. In the second simplex tableau, you will still have S1 in the basis column, but S2 will be replaced with the entering variable B. Next, we determine the pivot element, what is known as the pivot element. We are still in the process of developing the second simplex tableau. The pivot element is the element or entry at the intersection of the, now B is called the entering variable. The column containing the entering variable, which this column, is called the pivot column. And S2 is our outgoing variable. The row containing the outgoing variable or leaving variable is called the pivot row. Again, this is the pivot column. It is the column that contains the entering variable. And this is the pivot row. It is the row that contains the outgoing variable. And you look at the intersection of the pivot row and the pivot column. That number or that entry at the intersection of the pivot row and the pivot column is called the pivot element. And you can see that the element at the intersection of the pivot column and the pivot row is 10. This number 10 or this entry 10 at the intersection of the pivot column and the pivot row is what we call the pivot element. Again, this entry 10 is called the pivot element. It is the entry or element or the number at the intersection of the pivot column and the pivot row. And pivot column is the column that contains the entering variable. Pivot row is the row that contains the outgoing variable. In the second simplex tableau, the pivot element must be made 1 or must be changed to 1. And all the other entries in the pivot column except the first two entries, B and 7, and the last two entries must be made 0. Again, the pivot element must be changed to 0. And the rest of the entries in the pivot column except the last two entries and the first two entries must be changed to 0. So 10 must be changed to 1. And 5 must be changed to 0. Again, in the second simplex tableau, the pivot element must be changed to 1. And the other entries in the pivot column except the last two entries and the first two entries must be changed to 0. And that leaves us with only one element in the pivot column to be changed to 0, and that element is 5. Now to change this entry 10 to 1 and to change this entry 5 to 0, we apply what is known as elementary row operation. And there are 3 elementary row operations, and we will use them to convert 10 to 1 and 5 to 0. If you have taken or if you have a background in the course linear algebra, then you must know what elementary row operations are. There are also what are known as elementary column operations, but in the simplex tableau we only use the elementary row operation. Now to change this pivot element to 1, this is the elementary row operation that you will use. Again, to change an entry or convert an entry to 1, we apply this elementary row operation. This is actually the first of the 3 elementary row operations where the entries of the original row are replaced by a scalar multiple of the entries of the original row. So this is the operation, elementary operation that we will use to change an entry or convert an entry to 1. Now, I said the pivot element must be changed to 1 in the second simplex W. But if we have to change 10 to 1, we must change all the entries in this row. So it's not only 10 that will be changed to 1, the rest of the entries in the row containing the pivot element will change. And we apply this elementary row operation. That's why it's called elementary row operation, because we are operating on the entries of a row and not on a single element such as 10. In this elementary row operation, we are multiplying the R sub P. R sub P is the old pivot row. This is the old pivot row or the original pivot row. And to multiply the old pivot row with 1 over E, we multiply each entry of the old pivot row by 1 over E, where E here is the pivot element. In this example, our E is 10. Pivot element E is 10. In the second simplex W, the entries now of this row, or the new pivot row, R sub n, new pivot row, the new entries of the new pivot row in the second simplex W are obtained by multiplying the entries of the old pivot row by the reciprocal of the pivot element. If E is our pivot element, then 1 over E is the reciprocal of E. Again, to get the entries of the new pivot row in the second simplex W, we multiply the entries of this old pivot row by the reciprocal of the pivot element. And performing this elementary operation will change 10 to 1, as well as all the entries in this old pivot row. And we will do that now. We are now ready to construct the second simplex W, because we have identified the entering variable, which is the decision variable D. We have identified the outgoing variable, which is the second slack variable S2. And this is to be replaced by the entering variable B in the second simplex W. We also have identified the pivot element, which we defined as the entry or element at the intersection of the pivot column. The pivot column is the column containing the entering variable B and the pivot row, the row containing the outgoing variable. We have also identified the outgoing variable by dividing the entries of the last column or solution column or S column by the corresponding entries of the column containing the entering variable. And we said that the outgoing variable is the variable with the smallest positive quotient. In the second simplex W, the pivot element must be changed or converted to 1. And if we do that, we have to replace all the entries of the row containing the outgoing variable S2. And we do that by using the first of the 3 types of elementary row operation, given by Rn. R sub n is the row, the new pivot row containing the new entries of the pivot row. And the entries of the new pivot row can be obtained by multiplying the old pivot row R sub P by the reciprocal of E, and E is the pivot element and its reciprocal is 1 over E. In our particular example, the pivot element to be changed to 1 is 10. E is 10. And we perform this operation for us to know the new entries, the entries of the new pivot row. In the second simplex tableau, this column remains the S column or the solution column. The first two columns from the left remain the same, C sub j column, the basis column. And the last two rows remain the same, denoted by Z sub j, C minus Z sub j. The entries of the first two rows, the top two rows, remain the same, 6, 7, 0, 0. And the entries of the second row from the top, known as the variable row, remains the same, A, B, S1, S2. First, we determine the variables in the basis column for the second simplex tableau. We said that S2 is the outgoing variable. It will be replaced by the decision variable B in the second simplex tableau. And S1 will remain in the second simplex tableau. It will remain in the basis column S1. And we now replace S2, the second stock variable, with the decision variable B. Now we determine the entries of this new pivot row, which was originally the S2 row. By performing this operation, the pivot element is 10 and its reciprocal is 1 over 10. And we multiply the entries of the old pivot row by 1 over 10. The entries of the old pivot row are 7, 10, 0, 1, 70. We now multiply each entry of the old pivot row by the reciprocal of the pivot element, 1 over 10. And we will give the answers in fractions. And if you can reduce the fractions to lowest terms, you do that. 1 over 10 multiplied by 7 is 7 over 10. 1 over 10 multiplied by 10 is 10 over 10, and it's 1. 1 over 10 multiplied by 0 is 0. 1 over 10 multiplied by 1 is 1 over 10. And 1 over 10 multiplied by 70, that's 70 over 10, or 70 divided by 10 is 7. We now write these numbers in the row of B, which was originally the row of S2. And this is now the new pivot row with these new entries, 7, 10, 1, 0, 1 over 10, and 7. Now you can see that the pivot element 10 has been changed to 1. And also the other entries in the row of the outgoing variable have been changed to these entries 7 over 10, 0, 1 over 10, and 7. The next step is we must change this entry 5 to 0. And if we change 5 or convert 5 to 0, we have to change every entry in the row containing 5, or the entries of this row, S1 row. And we shall denote this by R1 or R or row 1. And the operation to change this 5 to 0 is this elementary row operation. Again, to change this number 5 or entry 5 or element 5 to 0, we perform this. This is the second type of elementary row operation. The R sub I is the ith row, to be replaced by a scalar multiple of the new pivot row plus the ith row. A here is the number to be changed to 0. In our example, A is 5, because 5 has to be changed to 0. R sub I is the row whose entries are to be changed to 0. R sub I is the row containing 5. In our example, R sub I is this row, which we denote by R1 or row 1. And this will be row 2. This is our row 1. Row 1 is the row containing the number or element to be changed to 0. And R sub n is the new pivot row with these new entries, or these new entries in the row of B. So we perform this operation. R sub I is row 1, the row whose entries are to be changed, and the row that contains the number to be changed to 0. Now, R1 now is to be replaced by performing this elementary row operation. We have minus A is 5, so we have minus 5 multiplied by the entries of the new pivot row plus the entries of row 1. This is row 1, its entries are 9, 5, 1, 0, 45. We perform this operation, negative 5 multiplied by the entries of the new pivot row, 7 over 10, 1, 0. This is the first term, negative 5 multiplied by R sub n, negative 5. R sub n, the entries are 7 over 10, 1, 0, 1 over 10, and 7. Plus the entries of row 1 in the preceding simplex tableau. This is our row 1. The entries are 9, 5, 1, 0, 45. So we write plus 9, 5, 1, 951,045 are the entries of the row 1 or R sub 1, whose entries are to be changed because we have to change 5 to 0. Now we perform these operations. We distribute negative 5 to these entries of the new pivot row. We multiply each entry of the new pivot row by negative 5. Negative 5 multiplied by 7 over 10 is negative 35 over 10. Negative 5 multiplied by positive 1 is negative 5. Negative 5 multiplied by 0 is 0. Negative 5 multiplied by 1 over 10 is negative 5 over 10. And we can reduce that to lowest terms by dividing the numerator negative 5 by 5 and dividing 10 by 5, and you get negative 1 over 2. Again, negative 5 multiplied by 1 over 10 is negative 5 over 10. And in lowest terms, it is equal to negative 1 half. And finally, negative 5 multiplied by 7 is negative 35. Plus these entries of the original entries of row 1. Plus 9, 5, 1, 0, 45. Now, you may use your calculator to get the sum. In most scientific calculators, you can add fractions. Negative 35 over 10 plus 9. Negative 35 over 10 plus 9. But if you do not have a calculator, you can add this mentally. For 9 to have a denominator of 10, you multiply 9 by 10 over 10. And the common denominator now is 10. And you can do this in your head. 9 multiplied by 10 is 90 minus 35. 90 minus 35 is 55. Positive 55. And again, we can reduce this to lowest terms. Do not use decimal numbers. Use fractions in lowest terms. 55 over 10 is 55 and 10 is divisible, are both divisible by 5. So we divide 55 by 5, you get 11. And 10 is divisible by 5, 10 divided by 5 is 2. Hence, negative 35 over 10 plus 9 is 11 over 2 in lowest terms. And negative 5 plus 5 is 0. 0 plus 1 is 1. Negative 1 half plus 0 is negative 1 half. And negative 35 plus 45 is 10. These are now the new entries of row 1 in the second simplex tableau, or the row of S1. We write them 11 over 2, 0, 1, negative 1 half, and 10. You can see that this 5 has been changed to 0, and all the entries in the row containing the number 5 have been changed to 11 over 2, 1, negative 1 half, and 10. Now we are to find the entries of C sub j and C minus C sub j. First, the entries of C sub j column. The entry here is the coefficient of S1, the first lock variable in the objective function 0. And the entry here is the coefficient of the decision variable b in the objective function. This b, its coefficient in the objective function is 7. Now we find the entries of this row C sub j in the same way that we find the entries of C sub j in the initial simplex tableau. We multiply the entries of each variable column by the corresponding entries of C sub j column, and we add the products. We have 0 multiplied by 11 over 2 is 0, plus 7 multiplied by 7 over 10 is 49 over 10. 0 multiplied by 11 over 2 is 0, plus 7 multiplied by 7 over 10 is 49 over 10. 0 plus 49 over 10 is 49 over 10. Next, 0 multiplied by 0 plus 7 multiplied by 1. 0 multiplied by 0 is 0, plus 7 multiplied by 1 is 7. We have 0 plus 7 is 7. Next, 0 multiplied by 1 is 0, plus 7 multiplied by 0 is 0. We have 0 plus 0 is 0. Next, we have 0 multiplied by negative 1/2 is 0. And 7 multiplied by 1 over 10 is 7 over 10. Hence, we have 0 plus 7 over 10 is 7 over 10. The last column, we multiply by the corresponding entries in the C sub j column. 0 multiplied by 10 is 0, plus 7 multiplied by 7 is 49. Thus, we have 0 plus 49 is 49. Finally, the entries of the last row, C sub j minus C sub j. This is the C sub j row minus Z sub j row. This 49 entry is not included. We have 6 minus 49 over 10. Again, you can get this difference using your scientific calculator, or you can do it mentally. For 6 to have the denominator of 10, multiply 6 by 10 over 10. And the common denominator now is 10. In the numerator, we have 10 multiplied by 6 is 60. Minus 49, and you get 11. Is that correct? 60 minus 49. 10 minus 9 is 1. And 5 minus 4 is 11. 11 over 10. 6 minus 49 over 10 is 11 over 10. And 7 minus 7 is 0. 0 minus 0 is 0. And 0 minus 7 over 10 is negative 7 over 10. And we do not have an answer for this cell because we do not have a number here, minus 49. We cannot perform that difference. This is now the complete second simplex tableau. And for the second simplex tableau, there is a corresponding new solution, and we call it the second solution. In the initial simplex tableau, we had our initial solution where the values of the variables, the values of the variables in the solution are given by the entries in the last column or solution column. For the initial simplex tableau, in our initial solution, S1 is equal to 45, S2 is equal to 70. And we said that those variables that do not appear in the basis column have values of 0. Thus, for the initial simplex tableau, the decision variables A and B did not appear in the basis column, and hence their values are 0. And we also said that the value of the objective function is given by the last entry in the last column. Here's the last column, and the last entry is 0. And that's the value of the objective function. And we do the same for the second simplex tableau to write our second or new solution. We start with the variables in the basis column. The values of the variables in the base column are the corresponding entries in the solution column or S column. Hence, in the second solution, the value of S1 is 10. The value of the decision variable B is 7. All the variables that do not appear in the basis column have values of 0. We do not find the decision variable A in the basis column, hence the value of A is 0 in the second solution. We also do not find the second slack variable S2 in the basis column because it was replaced by the decision variable B. Hence, the value of the second variable S2 is 0. And the value of our objective function now is 49. The last entry in the last column is the value of the objective function. And I think we use capital P in our objective function. The value of P is 49 for the second solution. You should notice that as you go from the initial simplex tableau to the second simplex tableau to the next simplex tableau, if there is a next simplex tableau, the value of the objective function should be increasing. It should continuously increase until you reach the maximum value of the objective function. Initially, the value of our objective function is 0. And in the second solution corresponding to the second simplex tableau, the value of the objective function is now 49. Thus, there has been an increase in the value of the objective function from 0 to 49. Because in the second solution corresponding to the second simplex tableau, one of the decision variables, B, has now a value of 7, although A remains 0. Now, how do we know if we are done with the solution? This is the test. You always look at the entries in the last row. The last row is C sub j minus Z sub j. And you look at the entries in the last row. As long as there is a positive entry in the last row, the solution is not yet complete. Again, to determine if you are done with the solution, look at the entries of the last row. The row C sub j minus Z sub j. if there is a positive entry in the last row, at least one positive entry in the last row, it means that the solution is not yet complete. And there will be a next simplex W. And in our second simplex W, there is one positive entry. The other entries are 0 and 0 and negative 7 over 10. But we only consider the positive entries in the last row. Since in selecting the entering variable, we only consider the positive entries, and if there are two or more positive entries, you take the highest or the most positive entry in the last row. Since in the last row there is only one positive entry, our entering variable is variable A. Because the positive entry 11 over 10 is under the decision variable A. So in the third simplex W, the variable A will enter the basis column. And for the variable A to enter the basis column, one of these variables has to go or to leave the W. It's either S1 or D. And to determine the outgoing or leaving variable, we divide the entries of the last column by the corresponding entries of the column containing the entering variable. And the smallest quotient and the entering variable will be the variable with the smallest positive quotient. We will do that test now. We now determine which of these two variables will be our outgoing variable or leaving variable. And to determine the outgoing variable, we divide the entries of the last column or the solution column or S column by the corresponding entries of the column containing the entering variable A. We divide 10 by 11 over 2. To divide 10 by 11 over 2 is to multiply 10 by the reciprocal of 11 over 2. Hence, 10 divided by 11 over 2 is equal to 10 multiplied by the reciprocal of 11 over 2, which is 2 over 11. Again, 10 divided by 11 over 2 is the same or equal to 10 multiplied by the reciprocal of 11 over 2, which is 2 over 11. And we multiply 10 times 2 is 20 over 11. And you can use your calculator to divide 20 by 11 up to at least 2 decimal places. Let us try to divide 20 by 11 manually. 20 divided by 11 is 1. 1 times 11 is 11. 20 minus 11 is 9. We add 1 decimal number 0. 90 divided by 11 is 8. And 8 multiplied by 11 is 88. 90 minus 88 is 2. We add another 0. 20 divided by 11 is 1. So 20 over 11 is approximately 1.81. Next, we divide 7 by the corresponding entry in the column of the entering variable. 7 divided by 7 over 10. And this is the same as multiplying 7 by the reciprocal of 7 over 10, which is 10 over 7. Again, 7 divided by 7 over 10 is the same as 7 multiplied by the reciprocal of 7 over 10, which is 10 over 7. And 7 over 7 will cancel out because it's equal to 1. And we get simply 10. In selecting the outgoing variable or the leaving variable, we take the variable with the smallest positive quotient. Among the positive quotients, you select the smallest positive quotient. Again, in the selection of outgoing variable or leaving variable, we do not consider the quotient that are negative, 0, and undefined or not defined. You only consider the positive quotients and you take the smallest positive quotients. In our example, there are only 2 positive quotients, so we take the smaller of the 2 positive quotients. The smaller between 1.81 and 10 is 1.81. And 1.81 is in the row of S1. Therefore, S1 is our outgoing variable or leaving variable. In the third simplex tableau, the variable S1, the slack variable S1 will be replaced by the decision variable A. But the decision variable B will remain in the third simplex tableau. And S1 will be replaced by A in the third simplex tableau. Now this column is the pivot column. This is the pivot column, the column containing the entering variable A. And this row S1, row 1 or the row of S1 is the pivot row. The pivot row is the row containing the outgoing variable or leaving variable. And the element at the intersection of the pivot column and the pivot row is 11 over 2. 11 over 2 is our pivot element. It is the element at the intersection of the pivot column, the column containing the entering variable, and the pivot row, the row containing the outgoing variable or leaving variable. In the third simplex tableau, this pivot element has to be changed to 1. And to change that to 1, you make use of the first elementary row operation to determine the new entries of the new pivot row. And the rest of the entries in this pivot column, except the last 2 entries and the first 2 entries, have to be changed to 0. Again, the pivot element has to be changed to 1. The other entries in the pivot column have to be changed to 0, except the last 2 entries and the first 2 entries. And that leaves us with only 1 entry in the pivot column to be changed to 0, which is 7 over 10. We change or convert 7 over 10 to 0 by using the second elementary row operation. For your practice and assignment, please develop the third simplex tableau from the second simplex tableau. We have already identified the entering variable A, the outgoing variable S1, the pivot element to be changed to 1, and this entry to be changed to 0. And from your third simplex tableau, please write the third or the new solution corresponding to the third simplex tableau. And there should be an improvement in the value of the objective function. From 49, you should get a higher value of the objective function. And then you check if there will still be a fourth simplex tableau by looking at the last row If there is still positive entry in the last row, that means your solution is not yet complete. And you have to develop the fourth simplex tableau. But if in the third simplex tableau, all the entries in the last row are either 0 or negative, that means you have reached the optimal solution or the best solution, which is the final solution. And that completes our lesson for today. If you have questions about the lesson today, you ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure. Or you may ask your friends and classmates to subscribe to my YouTube channel so they may learn as well. Thank you for joining me in my class today.